Excellent. Thank you for the opportunity to speak today. I'm Andy Nicholas. I work at the Space Science Division at the Naval Research Lab in Washington, D.C. I'm going to talk to you about an instrument concept we have for plume-surface interaction. Next slide. So a little background. We've developed an innovative sensor to really look at small object detection. It was funded by NASA's Heliophysics Division to look at orbital debris from low Earth orbit. We actually just delivered that sensor to the spacecraft about 6 weeks ago. It's integrated on the STP-7 spacecraft, should launch next September. But we're looking at taking the same technology and applying it to some lunar surface science. We think we can use it to observe and characterize plume surface interaction. We could also look at 2 other applications that I don't have time to talk about today, but look at micrometeor impacts and the associated dust ejecta that would come up from those, and observe and characterize levitating dust on the surface of the moon. So if anybody has questions on how we would do those last 2, please feel free to reach out and we can have further discussion on that. And I'll talk about that first application. Next slide. So the way the Laredo is the orbital debris sensor. It's super simple the way it works. Dan gave a good intro to active illumination sensing. That's what this is. So we take a continuous wave laser, we shine it off a diffusive optic and make a sheet of light. We wait for that an object to pass through that sheet of light and scatter some photons to our camera. That's basically how we make our detection of that. The nice thing about it is it's scalable. If I've got more laser power I can put to the light sheet, it will increase my sensitivity to either smaller or faster objects, or cast a wider net that I'm sensitive to. We're pretty excited about the delivery to STP-7. Like I said, that's through the DoD Space Test Program, and will launch next September. So that the technology and the components of that sensor are all already at TRL-6 since we've delivered, gone through all our environmental testing, and we hope to get to TRL-9 next September. Next slide. Very simple setup. For that case, we were using a 30-watt optical laser at 793 nanometers. It's a continuous wave laser. We chose that wavelength because it's very efficient, close to 50% efficient. So we put in 60 watts, we get 30 watts of light output out. Goes by fiber optic to a collimator, then to what we're using is a Powell lens that basically creates a sheet of light for us that allows us to see particles passing through that sheet of light. Next slide. So this is actually some testing of the Laredo sensor out at NASA Ames. I just wanted to show you that we have been capable of sensing pretty small objects. These are ranging from 0.5 millimeter out to about 3 millimeters, moving pretty quick. In the upper left of each plot is the speed the particle was moving at. The lower left is the size of the object, and you can see the traces going through these zoomed in pixels on the camera. So these range from like 2-ish kilometers per second out to about 5 or 5 and change kilometers per second. Very cool. We were able to see these things. I'm a big proponent of showing all my data, so we don't always get everything. Sometimes the cameras didn't work, the interfaces didn't work, so I show we get no data on a couple of them. And on those 4 on the bottom left row, we were changing the angle of things as they come through, so we can actually, just from watching it pass through the very thin laser sheet, about a 0.4 degree sheet for this particular system. It's a 55 degree fan, about 0.4 degrees thick. We can actually see, we can pick angles up out of that. Next slide. So the laboratory testing we've done at NRL, we have done some extensive testing in the lab to characterize how the system works. We basically are using different particles to shoot through. We'll use soft air pellets. We use 177 caliber lead pellets. We've used sand. We've used water mist, and we've tested this in the lab and shown we're pretty sensitive to these things at pretty decent speeds in the lab, up to about 100 meters per second. So Phil Metzger gave me some Starship modeling, particle size versus average particle velocity curves that you see there in the line plot. The green shaded area is the region we've already tested at NRL using sand, water, mist, and droplets, and larger objects. moving through all the way up to, say, 100 meters per second at the lab for that. Next slide. Some of the testing that we've also done, and we're going to do some more testing coming up in November, is we're going to go back out to the Ames vertical gun range and use the setup there. So out there, they have the capability to shoot things pretty fast. They can range from 0.5 kilometer per second up to about 6.5 kilometers per second. So the idea is we're going out there to do a little bit more testing for the orbital debris program, but I want to dedicate several shots to try to simulate some plume-surface interaction data. So this is what the system looks like. The big orange thing is the actual gun rail. It's shown in the vertical position here. So the two orange supports on the side, and then the vertical rail is the actual gun. They can raise and lower that and shoot at different directions. This is shown in the vertical position, shooting straight down into a chamber that's like 8 feet wide and maybe 10 feet high. You can see we've got our CAD set up here showing what our system looks like with the laser sheet going through there. Next slide. And here's the inside of the chamber with our laser sheet set up in there and a plumb bob showing where the shot's going to come from, and then a test of myself on the far right and the rest of the crew, Nestor, Josh, and Ken from left to right. We were doing an angled shot in that picture on the right, so we were setting up for that. You can see the string coming out of the wall in the background, coming to the center of the floor in the foreground. So we were doing an angled shot there. Next slide. So we're using neuromorphic cameras on these. So event-based cameras, those of you not familiar with those, instead of like a traditional frame-based camera, an event-based camera basically takes, you get data from every pixel. Each pixel operates independently and asynchronously. So you basically get a stream of data. If the value of that pixel went up, the brightness went up, you get a 1. If it went down, you get a 0. If the brightness of that pixel didn't change, you don't get any data. So you basically get a stream of time and then the X and Y of the event, and did it go up or down, the polarity of the event. Much easier to see the data when you view it as raw data. So we took some shots that were very small particles. I showed 2 examples of this, 0.5 millimeter spheres, and then we actually took some actual paint chips and chopped them up into little 0.5 millimeter, 1 millimeter paint chips. The data from our cameras is shown below that in reconstructed images. And then the image on the right is the NASA AVGR spark gap photo. It's a 40 nanosecond image, and you can see that little flotilla of paint chips flying in front of that big disc there. If we can cut out and show the movie, I think there's a separate file I had for the movie. This is what the data looks like in time, X and Y. If you just play that, I just rotate that around. You see these are up events as things move on, and as it goes to different angles, you can actually, your eye picks up the traces of the individual paint chips in that video very well. So we're mining that data, and this is where we think we can really help out with measuring the plume surface interaction. So the idea is when we go back out, you can go back to the presentation. If we go back out to NASA Ames and we can fill these little cup carriers, they're 3/16 of an inch wide, and we can fill them up with stuff. So we're going to get some simulated lunar regolith and try and shoot that through at like 500 meters per second to 1 kilometer per second, and show what kind of how sensitive we are to those size objects. Next slide. So this is kind of what our ConOps we think would look like. We could land and deploy a system, 250 to 500 meters. That's just my guess at where it would be a good spot. Set it up, watch during the descent or watch during an ascent. Collect the data, get that back, and then maybe pick the instrument up, stick it back inside a rover, keep it charged and warm until we're ready to use it again for another site. So that's basically our idea. I'll open up to questions or comments.